All right, let's do another one. This is a continuation of building up our 2D truss matrix analysis program. Last time we talked about the function EK truss 2D. Yeah, we did an example. It's right here. You let the program know where your node I and node j in here is 1 and 2 are, and give it a give it e. It'll calculate the L, theta, whatever, sine, cosine. Then it'll return you the element stiffness matrix. So now let's do another one where we will actually take in a truss structure. The truss structure, and then we need to assemble their global stiffness matrix. If you've been to my lecture, you know what I'm talking about. If not, I mean, yeah, you need to really take the lecture to know what I'm doing here. So basically, we need a function that will give us a result, which is the global stiffness matrix GK of truss 2D. Okay. The input is pretty cool. First, like I discussed in the class, and you know it, we need to know how many truss members there are. So there are m of them. Then we need to know how many nodes there is. So let's see, it's n. Let's do capitals. Because you know they are like numbers. Then we will need to have our a vector, and we need to have our e vector. What are the? Is the area of each of your m members. So A should be A1, A2, A3, all the way to AM, and E is same. This will accommodate the situation where the trusses are made out of different size members and different material. Then we'll have our node XY. That is the matrix we store our nodal coordinates. So the first row will be the x1 and y1. The second row will be x2 and y2. It'll have a total of n rows because you have n loads. And the final row will be xn and yn. And then finally we need our connectivity. We'll say it's con. Or short for connectivity. This guy basically tells you for each of these m members how are they connected. Like maybe the first member is connecting node number 1 and node number 5. Then that's your first element number 1. Again, this guy is a matrix. Right, the connectivity matrix. The number of rows is equals to the number of elements you have. Then the number of column is 2. Yeah, you just need one node and another node. Let's go ahead and do it. What happens is that we, like I said, eventually we want GK, but we want to know how large is the GK. Because the 2D truss, we have n nodes. Each node can move in 2 directions, so that's a total of 2n degrees of freedoms. So you can do your GK. Oh, come on. No. Okay. You can do your GK is a matrix. You can do like ones. This will generate all one matrix. You can say 2. Some people like to have 2n. Unfortunately that won't work because MATLAB don't know 2n what that means. It's 2 times n. Okay. and then 2 times n. So this will give you a 2n and 2n matrix full of 1. Then you time that by 0 to give you an empty 2n by 2n matrix. Now I'm gonna use that method of expanding the element stiffness matrix and then put them cumulatively into this empty GK1 until I've gone through all the elements. So we cover this in class. I'm just gonna do it. So basically, we'll say do a for loop, and then we're gonna do this for every single element. So we're gonna go 1 through how many elements you have, and then we'll first end it so that we don't forget. Then we'll come back and fill in something. So for each one, we'll say, okay, the first thing we need to do on each loop is, generate a temporary empty, what I say, EK that is expanded to GK size. Yeah, we talk about that in class. This can be done, in fact, very easily. We just call it temp EK equals to, it's gonna be expanded to GK size, so it is essentially this. So you can either just do this. Well, actually, you know what? This is good enough. So every time the temp EK will be like whole bunch of zeros. Now the next thing we need to do, we need to generate the EK for element II. Remember, II goes through 0, 1 to m, so it'll be element 1, 2, all the way to m. So how do you do that? You call your friend function, like, this guy, you already did it. So, okay, I'm just gonna call it. Ctrl C, come here, Ctrl V. We just say, it's not temp EK. I just say this guy's, or just temp EK small, okay? Then temp EK, this guy is expanded, but this guy is just 4x4. Just like the 4x4 is going to be output by here. But now the problem is that, what is this? Those two guys are easy because you're doing the II's element. So it's naturally you just take the II's material property. But how about those guys? Those are the node 1 and 2 of the element II. But what are they? So you're like, okay, I don't know. I'll just type them. I know I need them. But I have to find them somehow. So once I find them, then it's fine. The really kind of a funny part is first you need to know which two nodes your element is connecting. I got it. It's connecting. It's in this connectivity matrix. So maybe do this. Okay, first I need to say A equals to connectivity the ith row of 1. This is A is actually representing the first nodal number of the ith element. Then you can see what I'm doing here. The B apparently gonna be 2, so that's the Y. This is the this is the this is the node. Actually, it's a node number of 1. Oh, come on. Then this is the node number of 2. Then the actual coordinate of those nodes will actually be in the nodal XY matrix. Then you just need to pull them. So nodal XY, then if you want to pull X, you know you're going to pull from the first column. But this is the first node, right? So it's A. Yeah, I mean, it's as simple as that. And this is 2. And then this is B. This is B, and then 2. I will actually highly recommend you, like, I have a piece of paper, I have those things like written down for a simple example. Then look through these codes. You understand. Those codes, they pull the XY coordinates for the ith element. Then you got the EK, okay? Now remember, we need to kind of put the EK terms in expanded EK. In this case, it's the temp EK. But how do we know where to put it? We'll here use a pretty fancy technology. Yeah, it's not a fancy technology, but anyway, it's a fancy thing. We call it location. Basically, we'll say where the location is, right? The location is actually, it's on your notes. It's 2 times A minus 1. Then 2 times A. Then 2 times B minus 1. Then finally 2 times B. Okay, that's the location vector. That what actually that location is. So now it's time to put things in. Okay, so basically you do another for loop. For from JJ from 1 through 4. Then you do another loop for KK from 1 through 4. And then you do the end, close it. Yeah, in this class, when you see 2 for loops, you know we're looping through a matrix. The matrix we're going to loop through is actually the EK small matrix. So we just need to use one sentence because we're looping, this guy has 16 terms, and then we're looping this 16 times. So this one sentence is really simple. It's the temp EK, which is our expanded EK matrix. Its element is we just make it equals to the temp EK small, which we know is 4x4. Then not JJ and KK. Yeah, I don't use II because II is it's being used. It's within this loop. So the question is like, well, what is this? This is actually just loc JJ and then loc KK. Yeah, it'll do the magic. I mean, this goes through 1 through 4, and then here it'll actually pull from this location index map, and then map everything back in here. Okay, so after those, we can just say after these loops, the temp EK is ready. Then we just assemble it. So we basically have our original GK. GK equals to GK plus temp EK. Done. This is a cumulative add. If you have done any programming, you know this. This is a cumulative add. And then it's just a matrix doing cumulative add. Then remember, once you hit this loop back, then it will re-empty your temporary matrix, and then they'll redo this whole thing, and then it'll do it m times. Once it goes through that, you are done, and then you just need to output your GK. Okay, let's save this, and I'm really not gonna like do an example or something like that, because yeah, you guys try it out. Your program might be different than mine, but they should give the same results. Okay, that's it for this one.